Welcome to today's lesson, section 2.5 in our book, The Fundamental Theorem of Calculus. I know what you're thinking, this sounds like a very intimidating topic, but it's not that bad. It sounds intimidating because of the name. What it's really saying is that if you have a polynomial raised to a degree greater than 0, then you're going to have at least one 0, and another word for 0 is kind of like a solution. And the key part to that is the fundamental theorem of algebra applies to the complex number system. So you're going to have, in prior classes you're saying, oh, I've solved quadratics where there's no solution. Yeah, you're right, there is no solution in the real number system. But what we're going to be focusing on is, now that we did imaginary numbers, there's got to be at least one 0 in the complex number system. And so when you think of a complex number, complex numbers are set aside from real numbers. So you might say, oh, I've solved problems that don't have any complex solutions. The complex numbers also kind of fall into the category, while they're not real numbers. The definition for a complex number, which we covered last section, is a plus bi. That's a complex number. So if I made b equal to 0, well then this part doesn't really matter, and now I'm left with a, which is just a real number. So real numbers can be expressed using complex number notation. So while you've solved problems before that have, real number solutions, we're going to be looking at some that have complex solutions as well. Okay, so here, look at a problem that justify that f of x has exactly two zeros, x equals 3, and x equals 3. That's the same 0 twice. That's not a typo. All right, prove that 3 is a 0 twice. Well, how would you find the zeros of x squared minus 6x plus 9? I'm hoping you're saying factor. If you're not saying factor, you could say quadratic formula, but that's longer. So I'm hoping you're realizing this factors to two parentheses. So we would say x and x. If you're trying to find the zeros, you're going to set it equal to 0. Looks like minus 3 and minus 3. That is factored correctly. So what are our two zeros? Well, if I set my two equations equal to 0, using the zero product property, add 3 to both sides. Cross out. X equals 3 is one of your zeros. You have the same exact work here. You have x equals 3 as a 0 twice. You've shown it. Let's keep it rolling. All right, so now it's a little trickier. Find all the real and the complex zeros. So here's where you're still going to be using quadratic formula as an option. You're still going to be using factoring and solving. Here's one that I hope you're looking. You see a GCF here. If we're going to find all the zeros, I'm going to again set x cubed plus 4x equal to 0. And I'm going to say there is a GCF here. I can take out x, leaving myself with x squared plus 4 equal to 0. So I can set up, just like the last problem, I can set up, use the zero product property, set up x equals 0, x squared plus 4 equals 0. Now here's the tricky part. Okay, so I've got 1 0 here. In the past you might have said no solution to this. Yeah, no solution in the real number system, but there is a complex number that you can solve from here. And you get that by subtracting 4 to both sides. Subtract 4 to both sides. Fix that. Okay, so the 4's cancel. X squared equals negative 4. When you square root both sides, we should know the square root of negative 4 is plus or minus 2i. Square root of 4 is 2, and the square root of negative 1 is I, and then it's plus or minus anytime you take the square root of both sides. So this answer has 3 zeros. 0, 2i, and negative 2i are the 3 zeros to this problem. Alright, so an important point to this section, and something that will help you on every problem that you deal with zeros and complex numbers. All right, all complex zeros will occur in conjugate pairs, and let me explain what that means. That's saying if a plus bi if that is a complex number, the only thing you have to know is b cannot be 0, because if b is 0, then it's a real number. Then we don't. So as long as a plus bi, where b is not 0, if a plus bi is a 0, then a minus bi is also a 0. So that's the tricky part to every set. So for example, if you found that 3 plus 2i is a 0, then 3 minus 2i is also a 0 to that same exact problem. That only happens with complex numbers. It's not true for real numbers. All right, this only applies to complex zeros, not real numbers. So if 7 is a 0, that doesn't say anything about negative 7. It could be a 0, it's probably not a 0. But that only works for complex numbers. Okay, so here, find a 4th degree polynomial function with real coefficients that has negative 1, 1, and 3i as zeros. Okay, so we've stressed in this class that zeros are very similar to factors. And if negative 1 is a 0, the question is, if negative 1 is a 0, how do we turn it to a factor? Well, x plus 1 is the factor that leads you to negative 1 as a 0. So these two statements right here, closely related. X minus 1 is the factor that leads to 1 as a 0. Great. This works out well. We have x minus 3i is a factor that leads to 3i as a 0. Okay, this is weird. I need a 4th degree polynomial. I need one more set of parentheses here. And it's the rule comes from the very previous slide. All right. If 3i is a 0, what else must be a 0? And I hope you're saying negative 3i must also be a 0. So if negative 3i is a 0, well then what factor does that turn into? How does that relate to a factor? And that's going to be the x plus 3i. So here are all of the factors, and now to turn this into a 4th degree polynomial, I need to do one big FOIL. And the part I'm going to stress is using a difference of squares is a huge help here. Why do I say that? Is because when I look right here, I see those are a difference of squares, and you know what? If you're really fancy, those are a difference of squares as well. So we should be able to simplify this in an easier way if we look for difference of squares first. Okay, because this is a difference of squares, that's x squared minus 1. That's what that's going to FOIL to. Over here, I do have a difference of squares. X times x is x squared. Now some people are going to write minus 9i squared, but going back to yesterday's lesson, we're never going to leave I squared in an answer. I squared is equal to negative 1. So overall, that's going to turn that whole piece into plus 9. Now this is still, to make this a 4th degree polynomial, I have to do one more big FOIL, which means x squared times x squared is x to the 4th. X squared times 9 is plus 9x squared. Minus x squared minus 9. That's going to be x to the 4th plus 8x squared minus 9. That would be, if you didn't believe me, you could actually factor that and get zeros, negative 1, 1, 3i, and negative 3i. So that's one way you could check your answer, although it'd be a lot of work. Okay, let's keep moving on. Write f of x as a product of linear factors, then list all the zeros. So find all the factors, find all the zeros. All right, when we see very large, something raised to a very large power, it's not going to be easy. We could use the rational root theorem and get some guesses from there. We could try to guess some and use synthetic division, but that's all tough and a little bit of guesswork. So what I'm going to recommend here is we can actually go to a calculator, and I think in advance right here, I've already entered our function here into the calculator. You can do the same if you have one at home. Enter into the calculator. What I'm going to do next is I'm going to put a normal standard graph onto that, and the calculator is going to graph, and I should be able to get at least estimates for what look like they might be some possible roots. In fact, I might want to zoom in, hit the zoom key, and if I go down to zoom standard, option 6, hit enter. Oh, I'm sorry, I did the wrong one. I wanted to zoom in there. So let's go back to that. Let's go, sorry, option 2, zoom in. I'm sorry, I hit the wrong one. Hit enter one more time, and your calculator will zoom in. And now you can see it looks to me like, I'm going to copy this over onto the page. It looks to me like negative 2 is definitely a 0. Over here, it looks like 1 is a 0, but because the graph just touches and doesn't pass through, I'm going to say 1 might be a 0 twice. So when we look for some zeros, it looks like 1 is going to be a possible 0. So if we think 1 is a 0, then we're going to use our synthetic division. So 1, 0, 1, 2, negative 12, 8. We're going to use our synthetic division and prove that x minus 1 is a factor and that 1 is a 0. Now notice those two, again, closely related, just like the last slide. So synthetic division, this is going to go quick. Add up, carry over, add them together. Multiply by 1, it's still 2, add them up. Multiply by 1, it's still 4, add them up. Negative 8, multiply by 1, and we get our remainder of 0. This concludes 1 is definitely a 0 here. We believe that 1 is a 0 of multiplicity 2, so we're going to keep going. We're going to do this again. We're going to do another division. See if x minus 1 is a factor one more time. See if 1 is a 0 one more time. So again, we're going to take it out twice because we think it's multiplicity 2. That's going back to why the graph just touches and does not pass through. So the same similar multiplication and add, multiply and add. I don't need this 0 here anymore if that confuses anyone. I get positive 8. This time I get a remainder of 0 again. So I have found yet another. So 1 was actually a 0 twice. I'm going to keep going. We also believed that negative 2 was a 0. That's saying we believe that x plus 2 is a factor. So we are going to test, you guessed it, we are going to test negative 2 as a 0. And notice, I'm not going back to the original problem. I'm continuing to divide into, divide out pieces.
Please report to the main office. William Andy to the main office, please. Thank you.
I'll get the 0 out of that. So again, if you got that, I'm continuing to divide out factors each time. Continuing every time I find a 0, I'm dividing out one more factor. So a quick synthetic division. Take down the 1, multiply. It's negative 2. Add them up. That's 0. 0 times negative 2 is 0. Add them up. That's 4. Negative 8. And now I get 0 as a remainder. So far, I have found out that x minus 1 was a factor. It was a factor twice. And x plus 2 is a factor once. What I'm left with is this statement here. This is my x squared term. This is my x term, which I don't really need to worry about because there's a 0 here. So I have x squared plus 4. The question is, this is completely factored. I'd like to go one more step further and actually find all my zeros. Well, we've talked about them so much, I think we can say x equals 1 is a 0, x equals 1 is another 0, x equals negative 2 is a 0. Here, you would say x squared equals negative 4, which is going to say, when you square root both sides, x equals plus or minus 2i. So the other two zeros, x equals 2i, and x equals negative 2i. Notice our conjugate pairs of if 2i is a 0, negative 2i must be a 0. We're going to finish this up with one more problem in the next section.